Good morning, everyone. Thank you for joining us today.
Good morning. Great to be here.
In our last deep dive, we delved into the fascinating world of Internet of Things platforms and their cloud integration. Really foundational stuff.
Absolutely. Setting the stage, for where things are heading.
Exactly. And today, we're taking that conversation a significant step further, exploring a crucial architectural evolution: edge computing and fog in Internet of Things.
Yeah, this is where things get really interesting, moving beyond just connecting devices to making them, truly intelligent locally.
It really is. This deep dive is tailored to clarify the complex concepts of distributed computing that are rapidly reshaping the IoT landscape, hopefully giving you a shortcut to being truly well-informed.
It's a truly exciting area, and as we push the boundaries of what IoT can achieve, understanding these distributed architectures becomes absolutely vital. Think of it as intelligence moving closer to the action.
That's a great way to put it. Intelligence closer to the action. And to ensure we cover all the essentials, we're going to lay out our roadmap of core questions up front. We'll tackle these one by one.
Sounds like a good plan. Gives everyone a clear picture of what we'll cover.
Right. We want to give you a complete nuanced picture of this profound shift. So here are the 14 questions we'll be addressing today. First, how are edge and fog computing challenging the traditional cloud-centric IoT structure? Second, could you define the three models, cloud, fog, and edge? And perhaps use an analogy to explain the differences.
Good one. Those terms can get confusing.
Third, what is the single most significant advantage of processing data at the edge?
The big one.
Fourth, besides speed, what are the other key benefits of edge computing?
Always more than just speed.
Fifth, how does edge computing improve privacy and security?
Crucial these days.
Sixth, what happens in a cloud-only model if the internet connection goes down, and how does the edge help?
Reliability, yeah.
Seventh, how does this enable what the document calls real-time decision-making?
Moving from passive to active.
Eighth, can you provide the example from the text that contrasts a cloud-based system with an edge-based one on a factory bottling line?
Love that example. Really makes it clear.
Ninth, let's talk about specific use cases. How is edge computing used for predictive maintenance in a smart factory?
Practical applications.
10th, what about in healthcare? How does the edge help with real-time patient monitoring?
High stakes there.
11th, the document discusses the convergence of edge computing and AI. What is this field called?
The exciting frontier.
12th, how is it possible to run a complex AI model on a small, resource-constrained microcontroller?
Seems like magic.
13th, what are some examples of this edge AI in action?
Bringing it home.
And finally, 14th, to conclude, what is the key takeaway about the evolution from centralized cloud models to a distributed architecture?
Wrapping it all up. Okay, quite a list. Should be a good discussion.
All right, let's dive right into how this architectural shift is truly disrupting the status quo. Our first question explores: how are edge and fog computing challenging the traditional cloud-centric IoT structure?
Right. So what's fascinating here is how the traditional IoT architecture, the one our sources describe almost like a monarchy, with a big central cloud ruling everything.
Yeah, that analogy really stuck with me. Everything reporting back to the king, so to speak.
Exactly. And while that cloud model is incredibly powerful for, say, large-scale analytics, crunching historical data, finding long-term trends, it's being seriously challenged now by these more democratic distributed structures.
Democratic, I like that. Decentralized.
Precisely. Edge and fog computing, they fundamentally shift intelligence away from that central cloud. They push it closer to the outer fringes of the network, sometimes directly onto the devices themselves.
So it's less about reporting up and more about acting locally.
That's the core idea. It's about decentralizing that computational power, putting the processing closer to where the data is actually generated. Less travel time, quicker reactions.
That monarchy analogy really does paint a picture of this decentralization. But, for organizations already heavily invested in that traditional cloud model, what's the biggest, maybe, hurdle or potential downside they might face? Is it really a seamless evolution, or are there significant re-architecting challenges involved?
That's a really important question. It's not always a simple switch. While the benefits, as we'll see, are compelling, probably the primary challenge often lies in the operational complexity. You're now managing a distributed fleet of potentially thousands, even millions of intelligent devices.
Right, that sounds complex. Orchestration, security.
Exactly. It requires new tools, new ways of thinking about deployment, updates, and particularly security across all those distributed points. However, the fundamental shift in capability, it unlocks the real-time responsiveness. The reliability often outweighs these initial hurdles. The value proposition is just too strong in many cases.
Okay, that makes sense. The benefits drive the change, even with the complexity.
Right. So now that we understand why the structure is changing, let's maybe clarify what these new players actually are. You asked about defining the three models. Could you break down cloud, fog, and edge, maybe with those analogies?
Definitely. Let's start with the most familiar one, cloud computing. This is the model where basically all the data from your IoT devices, your sensors, travels over a network, usually the internet, a wide area network, to these huge remote centralized data centers. That's where the processing and analysis happen.
The big brain in the sky.
Kind of, yeah. The analogy we mentioned is like your brain's conscious thought. If your hand touches a hot stove,
Yeah.
right, the signal travels all the way up your arm through your nervous system to your brain.
Takes a moment.
Exactly. Your brain processes it, goes, ouch, hot, recognizes the danger, and then sends a command back down to move your hand. It's powerful, capable of complex reasoning, but there's always going to be some delay, some latency, just because of the distance that signal has to travel.
Right. That round trip takes time. And then the edge really changes that equation, doesn't it? It cuts out a lot of that delay.
It absolutely does. So edge computing is the most radically decentralized model here. Computation happens directly on the IoT end device itself, the sensor, the camera, the machine, or maybe on a dedicated gateway right next to it. It's truly at the literal edge of the network.
Well, there where the action is.
Exactly. And the analogy for edge, it's like the spinal reflex. Your hand touches that hot stove again, but this time, a reflex arc in your spinal cord triggers an immediate command. Pull your hand away. And this happens before the pain signal even fully registers in your brain.
Instantaneous reaction, almost subconscious.
Totally. It's an extremely fast, localized response designed purely for immediate action.
Yeah.
Like an edge device analyzing vibration data on a critical piece of machinery and triggering an emergency shutdown instantaneously if it detects a problem. No waiting for the cloud.
That's a powerful difference, essential for safety-critical stuff. So where does fog computing fit in? It's kind of this middle ground, right?
Exactly. It acts as that intermediary layer. Fog computing, a term originally coined by Cisco, actually it occupies that space between the super-localized edge and the distant cloud. It creates a sort of fog of computing resources, but within the local area network, the LAN.
So not on the tiny device, but still nearby.
Right. A fog node isn't usually a tiny sensor. It could be a more powerful device like an industrial PC on a factory floor or a local server in the building, maybe even a network router that has some extra compute capabilities built in.
Beefier than the edge device, but not the full cloud.
Correct. And its job.
Yeah.
It often aggregates data from multiple nearby edge devices. It can perform more substantial local processing than a single resource-constrained edge device could manage. And then, importantly, it communicates maybe summarized data or key alerts up to the cloud.
Okay, so it filters and pre-processes?
Yeah, think of it like the brainstem or the cerebellum in our body analogy. It handles more complex tasks than a simple reflex, but they're still somewhat localized, maybe subconscious things like coordinating balance, regulating breathing.
Got it. More complex coordination, but still local.
Right. So a fog node on a factory floor might be coordinating the complex movements of, say, a dozen robotic arms working together, optimizing their workflow in real time based on data from multiple sensors.
While maybe only sending overall production stats, the summary, up to the main cloud for long-term analysis.
Precisely. It manages the local orchestra, you could say.
Okay, that makes sense. Cloud, fog, edge, different locations, different capabilities.
Exactly. So just to quickly synthesize those key distinctions again. Cloud is remote, global scope, generally higher latency. Fog operates within the local network, medium latency, local scope, and edge is right there at the device. Very low latency, device-specific scope.
And that hierarchy impacts everything else too, right? Like bandwidth.
Definitely. Bandwidth usage generally decreases as you move down from cloud to fog to edge because you're processing more locally and sending less raw data upstream.
And connectivity requirements.
Also different. Cloud generally always needs that internet connection. Fog can often operate intermittently, maybe syncing up periodically. And edge devices, crucially, can often function fully offline if needed.
That offline capability is huge for reliability.
Absolutely. And it's really crucial, as you mentioned earlier, to understand that these aren't usually competing models. They're not mutually exclusive. The most powerful, robust IoT architectures strategically use all three together.
A hierarchy. A continuum of computing.
Exactly. Leveraging each layer, edge, fog, cloud, for its unique strengths. That's how you build a truly resilient and intelligent system.
Right, using the right tool for the right job at the right level. Okay, that clarifies the what's. Now let's zoom in on the why. You asked about the biggest win for edge. What is the single most significant advantage of processing data at the edge?
This seems fundamental. What really drives adoption?
Well, while speed or low latency is often the headline, I think the true game changer of edge processing is maybe slightly different. It's how it enables systems to make those instantaneous, sometimes life or death decisions without needing to phone home to a distant cloud.
So it's the autonomy enabled by the speed.
Exactly. It transforms IoT from just monitoring things to enabling truly autonomous, sometimes life-saving decision-making right where it matters. So yes, the single most significant technical advantage is unequivocally latency reduction.
Cutting out that round trip time.
Completely. By processing data locally, you eliminate that delay entirely. And in applications where every millisecond genuinely counts, think of an autonomous vehicle's collision avoidance system reacting to a pedestrian stepping out.
Can't wait for the cloud on that one.
Absolutely not.
Ugh.
Or a high-speed manufacturing line checking for tiny defects. Or a medical device responding instantly to a critical change in a patient's vital signs. In those cases, low latency isn't just a nice-to-have feature. It's a fundamental, non-negotiable requirement.
It's the difference between working and not working.
Precisely. Edge computing makes these real-time control loops possible. It allows immediate action based on local data.
Okay, latency is king. But you hinted there's more to it. Beyond just raw speed, what are some of the other really key benefits edge computing brings? Besides speed, what are the other key benefits of edge computing?
Yeah, there are definitely other major advantages. Another huge one is bandwidth conservation, and tied directly to that, significant cost savings.
How so? Less data flying around.
Exactly. Just imagine an industrial site, a factory, an oil rig, a wind farm with maybe thousands of sensors. These things can generate terabytes of raw data every single day.
Wow, terabytes. Try to stream all that raw, unrefined data continuously back to a central cloud.
Well, first, it's often technically challenging just because of network limitations, especially in remote areas.
Yeah.
But perhaps more importantly, it's also prohibitively expensive. Think about the costs of cellular data plans or dedicated internet bandwidth needed for that volume.
Yeah, the data transmission costs alone would be astronomical.
Right. Edge computing tackles this head-on. By processing the data locally, right at the source, you can intelligently filter it. You extract only the small, valuable pieces of information.
Like what? What gets sent?
Maybe just a summary statistic or an alert if something's wrong, or a key performance indicator, KPI. Only that small, condensed, valuable insight gets sent up to the cloud.
Instead of the fire hose of raw data.
Precisely. And the impact. Our sources suggest this approach can reduce bandwidth requirements by, get this, over 90% in many cases.
Over 90%. That's staggering. That translates directly to massive operational cost savings for businesses.
Huge savings. It makes deploying large-scale sensor networks economically feasible in a way that cloud-only models often don't.
Okay, so lower latency, massive bandwidth, and cost savings. That 90% figure really highlights the efficiency gain. Now, this must also have a pretty significant positive impact on data privacy and security, right? Keeping data local.
Absolutely. That leads perfectly into the next point. How does edge computing improve privacy and security?
Which is a massive concern for everyone these days.
It's a very critical aspect, especially with regulations like GDPR, PIPEDA in Canada, HIPEE for healthcare, becoming stricter all the time.
Yeah.
The fundamental issue is that transmitting sensitive raw data, especially over the public internet to a cloud, inherently introduces risk.
Risk of what? Interception.
Hacks, interception during transit, unauthorized access at rest in the cloud, potential breaches. The attack surface is just larger when data travels far and wide.
Okay.
So for applications dealing with highly sensitive information, think personal health information, PHI for medical devices, financial transaction data, proprietary industrial process data, even video feeds from inside a home, keeping that raw data on-premise, within the local network, or even just on the device itself, offers a major security and privacy advantage.
Makes sense. The less it travels, the less exposure.
Exactly.
Yeah.
With edge computing, the raw sensitive data can be processed and analyzed locally. And crucially, personally identifiable information, PII, or other sensitive details, can potentially be anonymized or completely stripped out before any aggregated or summarized data ever gets sent to the cloud.
So you only send the anonymized insight, not the raw personal data.
Right. This significantly helps organizations meet compliance requirements for those strict data privacy regulations we mentioned, like Canada's PIPEDA, the Personal Information Protection and Electronic Documents Act, which has strong rules about handling personal data. Processing at the edge helps contain that sensitive information.
That offers a huge layer of protection, particularly for industries like healthcare or finance, or anywhere dealing with personal or confidential info. Okay, another angle, reliability. Let's talk about connectivity. In a pure cloud-only model, what happens if the internet connection just goes down? And how does Edge provide a safety net? What happens in a cloud-only model if the internet connection goes down, and how does the Edge help?
Yeah, this is a really practical and often critical advantage of the edge. In a purely cloud-dependent system, if that internet connection fails, well, operations can essentially just grind to a halt.
Everything stops.
Pretty much. Think of a smart factory where the production lines rely on real-time instructions or monitoring data from the cloud. Or imagine a remote oil rig or agricultural sensors in a field that suddenly lose connectivity to their central monitoring system.
The whole system could become inoperable, blind and dumb, essentially.
Exactly. You lose visibility, you lose control. Edge devices, however, provide a critical safeguard here, ensuring increased reliability and offline operation. Because the intelligence is local, they can continue to operate autonomously.
Even with no internet.
Even with no connection to the cloud, they can keep collecting data, they can keep executing their local logic, like controlling machinery based on sensor readings completely independently.
What happens to the data collected during the outage?
Good question. They can typically store that data locally, often on internal memory or a small SD card. Then, once the connection is eventually restored, they can seamlessly sync that stored data back up with the cloud.
So no data loss and operations continue.
Right. It ensures operational continuity, which is absolutely vital in unpredictable environments, remote locations, or critical infrastructure, where you simply cannot rely on a constant, stable internet connection. It makes the whole system fundamentally more resilient.
So it's about making systems fundamentally more robust, less fragile, less reliant on that single point of failure, the internet connection. This sounds like it directly enables something the document specifically calls out, real-time decision-making. Moving beyond just monitoring, how does this enable what the document calls real-time decision-making?
Yes, real-time decision-making is really the ultimate payoff here. It's what truly transforms an IoT system from being just a passive monitoring tool, collecting data and showing dashboards into an active, intelligent participant that can actually influence physical processes as they happen.
From observing to acting.
Exactly. And edge computing is the core enabler for this because it allows for that incredibly tight sense-process-act loop we talked about earlier.
Can you break that loop down again?
Sure. The edge device senses the environment. Maybe a camera sees a defect on a product, or a sensor detects a pressure drop. Then it processes that data immediately, right there on the device, perhaps against a set of predefined rules, or even using an embedded AI model.
Okay, sense, process.
And then, based on that local processing, it instantly acts. It actuates a response signaling a robotic arm to remove the defective product, closing a valve, sounding an alarm.
All happening locally and quickly.
All happening within a predictable, deterministic time frame, often measured in milliseconds. This entire closed-loop control system occurs entirely at the edge, which completely eliminates the variable latency and the dependency of making a round trip to the cloud.
So you get guaranteed, immediate, and predictable outcomes without worrying about internet lag.
Precisely. That's real-time decision-making in action, enabled by the edge.
That sense-process-act loop really clarifies the mechanism. To make this even more concrete, let's use that example from the text. It contrasts a cloud-based system versus an edge-based one on a factory bottling line. Can you provide the example from the text that contrasts a cloud-based system with an edge-based one on a factory bottling line?
Oh, yeah, this is a great one for illustrating the difference. So imagine you've got this high-speed bottling line, bottles whizzing past, and you need quality control.
Right. Checking for defects, fill levels, whatever.
Exactly. In a traditional, purely cloud-based setup, you might have a camera that captures an image of each bottle as it goes by. Okay, step 1.
Capture image. Got it.
Step 2. That camera then needs to upload that image file, which could be quite large, all the way up to the cloud over the network.
Upload. Okay.
Step 3. Somewhere in that distant cloud data center, a powerful AI or image processing algorithm analyzes the image to check for defects.
Cloud analysis.
Step 4. If a defect is found, the cloud system then needs to send a command back down over the network again to maybe a robotic arm positioned further down the line, telling it to remove that specific faulty bottle.
Command back down. Okay, seems logical, but...
But here's the critical problem, especially on a high-speed line.
Oh.
The delay. The round-trip time for upload, analysis, and command download takes time. Maybe seconds, maybe fractures of a second, but by the time that remove command finally arrives back at the robotic arm.
The bottle's long gone.
Exactly. Literally hundreds of other bottles could have already passed by on that fast-moving conveyor belt. The delay makes the intervention completely ineffective. It's too late. You end up with defective products going out, or maybe you have to reject a whole batch later. Significant waste.
Yeah, that sounds incredibly inefficient. Hundreds of bottles missed.
Yeah.
That's a lot of potential waste or quality issues. How does Edge fix this?
Okay, now contrast that with an edge computing model. Here, you use a smart camera. This isn't just a dumb camera sending images. It has its own integrated processor right inside it.
Processing on the camera itself.
Right. It runs the AI defect detection model directly on the device. So, step 1, capture image. Step 2, analyze image locally, right there, in milliseconds.
Sense and process instantly.
Instantly. If it identifies a defect, step 3 is immediate. It sends a simple electrical signal directly to the robotic arm sitting right next to it on the line.
No cloud trip needed.
None. The signal goes straight from the camera's brain to the robot's arm, telling it, remove this bottle right now. The decision and the action are virtually instantaneous and perfectly synchronized with the physical process happening right there.
Wow. That's a night and day difference.
It really is. It's the fundamental difference between, reactively reporting historical events after the fact versus achieving truly real-time, proactive inline control. And the shift unlocks immense value in industrial automation, quality assurance, safety systems, you name it.
That bottling line example paints such a clear picture. Reactive versus proactive control. Okay, let's broaden out to some other specific use cases. You mentioned factories. How is edge computing used for predictive maintenance in a smart factory?
Predictive maintenance is a classic and really high-value use case for edge. So imagine you have a critical motor, maybe on an assembly line or powering a large pump. Unplanned downtime for that motor could halt the entire production line, costing a fortune.
Yeah, downtime is the enemy in manufacturing.
Absolutely. So instead of just waiting for it to fail, you fit it with a smart vibration sensor. Now, the sensor is constantly measuring the motor's vibrations, but instead of streaming that constant raw vibration data, which again would be an enormous amount of data, mostly noise, back to the cloud.
You process it locally?
Exactly. There's an edge processor, maybe right on the sensor itself or in a small nearby gateway, and it's running a specialized machine learning model.
An AI model for vibrations.
Yes. This model has been trained to analyze those complex vibration patterns in real time. It learns what normal looks like for that specific motor under different loads. And crucially, it's trained to detect the very subtle, often imperceptible to humans, changes in the vibration signature that indicate an impending problem, like a bearing starting to wear out or a shaft misalignment developing.
So it hears the problem starting before it becomes catastrophic.
Precisely. It can detect the early warning signs, and if it detects that signature of an impending failure, then it sends an alert. But not the raw data. It sends just a single, highly specific and actionable alert message up to the central maintenance system.
What would the alert say?
Something concise and useful, like, warning, bearing failure likely within the next 48 hours on motor B7, assembly line 3.
Wow. Specific and actionable.
Exactly. That allows the maintenance team to proactively schedule repairs during planned downtime, order the right parts in advance, and prevent that costly unexpected failure. All achieved while minimizing the data transmission, only sending the critical insight, not the terabytes of raw vibration noise.
That's incredibly efficient. Getting just the right, actionable information to the right people at precisely the right time. Huge value there.
Okay, let's switch sectors. What about healthcare? Privacy and speed are both absolutely critical there. How does the edge help with real-time patient monitoring?
Healthcare is another area where edge computing is truly transformative, precisely for those reasons, speed and privacy. Consider a patient maybe recovering at home after heart surgery, and they're wearing a smart patch that continuously monitors their ECG, their heart rhythm.
Okay, like a wearable ECG monitor.
Right. Now, instead of constantly streaming that highly sensitive raw ECG waveform data to a cloud server, which raises major privacy concerns and uses a lot of battery and bandwidth, there's an edge processor embedded within that patch itself.
AI on the patch.
Yes. It's running a sophisticated, optimized AI algorithm that's been trained specifically to detect dangerous cardiac arrhythmias, things like atrial fibrillation or ventricular tachycardia, directly on the device in real time.
Detecting problems locally. Exactly. If that onboard AI detects a dangerous pattern, it can trigger immediate actions. First, it might sound a local alarm right there on the patch, or send an alert to the patient's smartphone, alerting them, or a nearby caregiver instantly.
Immediate local warning.
Yes. And simultaneously, it can send a high-priority but condensed alert message, maybe just alert, suspected atrial fibrillation detected at timestamp up to the hospital's secure cloud portal or monitoring center, alerting the clinical staff.
So the doctors get the urgent alert, but not necessarily the raw data immediately.
Correct. Crucially, the raw sensitive ECG waveform data generally never has to leave the device and travel over the internet unless a doctor specifically requests it later for detailed diagnostic review. This approach ensures maximum patient privacy by keeping the raw data local while still enabling rapid, potentially life-saving intervention based on the AI's real-time analysis at the edge.
That's a really elegant balance. You get the immediate life-saving potential without compromising the patient's sensitive health data unnecessarily. A perfect blend of privacy and speed.
Exactly. It addresses both critical needs simultaneously.
Now, speaking of AI running on these devices, the document discusses this really fascinating convergence of edge computing and artificial intelligence. For many people, I think, AI still conjures up images of massive data centers, racks of GPUs, powerful cloud servers.
Yeah, the traditional view of AI needing huge resources.
Right. So what exactly is this field called, where AI meets the edge? And how does it reconcile this powerful AI capability with the idea of these small, distributed, often resource-constrained edge devices? The document discusses the convergence of edge computing and AI. What is this field called?
Yeah, that's a great question because it really does challenge our traditional understanding of where AI lives and runs. This convergence has given rise to one of the most exciting and maybe still somewhat underestimated shifts happening in AI today. The field is generally known as Edge AI.
Edge AI.
Makes sense. And a very popular and rapidly growing subfield within that, focusing specifically on running AI on very low-power devices like microcontrollers, is often called tiny machine learning or TinyML.
TinyML. I love that name. It almost sounds like a contradiction in terms, doesn't it? Given how much processing power and data AI models usually seem to need, it's kind of hard to wrap my head around running AI on something tiny.
It does seem counterintuitive at first glance.
So what's the secret sauce here? What's the magic trick? How is it possible to run a complex AI model on a small, resource-constrained microcontroller? You know, the kind of chip you might find in a simple appliance, not a supercomputer.
Right. It's not magic, but is very clever engineering. It's achieved through a sophisticated process generally known as model optimization. It's a multi-step process.
Okay, break it down.
So first, the large, complex AI model, say, a deep neural network for image recognition or voice processing, is initially trained in the traditional way, in the cloud or on powerful servers, using massive data sets and lots of processing power. That's where the model learns its task and builds its intelligence. That heavy lifting still happens centrally.
Okay, so training is still big and powerful.
Usually, yes. But then, once you have that fully trained, accurate, but large model, you apply specialized techniques to make it much, much smaller and incredibly efficient, specifically for deployment on those target edge devices, without losing too much of its core predictive accuracy.
How do you shrink it without breaking it?
There are several key techniques. Two of the most common are quantization and pruning.
Quantization and pruning. Okay.
So quantization basically involves reducing the numerical precision used within the model's calculations. Instead of using, say, 32-bit floating point numbers for all the model weights and activations, you might convert them to use 8-bit integers, or even fewer bits. This drastically reduces the memory footprint and computational cost.
Using less precise numbers, but it still works well enough.
Surprisingly well, often yes, with clever techniques. Then there's pruning. This is like trimming a bonsai tree. You systematically identify and remove redundant or less critical connections, the synapses within the neural network that don't contribute much to the final output.
Cutting out the dead wood, basically.
Kind of, yeah. It makes the network sparser and smaller. By combining techniques like quantization, pruning, and other architectural optimizations, you can create a highly efficient, compressed version of the original large model.
And this compressed version.
This compressed, optimized model can then run effectively on a low-power microcontroller, using only maybe a few kilobytes or at most megabytes of memory, and consuming very little energy. It's truly about distilling the essence of the AI's intelligence into a tiny, efficient, deployable footprint suitable for the edge.
That's truly incredible engineering, taking that massive intelligence and squeezing it down so effectively. Fitting so much capability into such a tiny, low-power footprint opens up so many possibilities.
Yeah.
Can you give us some concrete examples of this edge AI, this TinyML, in action? Maybe things we might even encounter or will soon in our daily lives. What are some examples of this edge AI in action?
Absolutely. We're actually seeing it pop up in more and more places, sometimes quite subtly, often without us even realizing there's sophisticated AI running locally.
Like what?
Well, think about a modern smart doorbell. Some of the newer ones can perform facial recognition directly on the device to tell you who is at your door, dad is at the door, without needing to constantly stream your front porch video feed up to the cloud for analysis.
Ah, so the recognition happens locally. That's great for privacy.
Huge for privacy. The video stays local unless there's a specific event you want to review. Another example. Some smart home appliances, like speakers or even microwaves, are starting to incorporate on-device voice command processing.
Meaning they can understand me even if my Wi-Fi is down.
Exactly. They can understand basic commands, turn on, set timer, using a TinyML model running locally, ensuring they still work and respond instantly, even without an active internet connection.
That's really useful. No more yelling at unresponsive gadgets when the internet flickers.
Right. And looking beyond the home, think about agriculture. You could have smart agricultural sensors deployed across a large field. One equipped with an on-device edge AI model could analyze images captured by a tiny camera.
What would it look for?
It could be trained to identify specific types of pests, like a particular aphid, or early signs of plant diseases directly from the image it sees. And based on that local identification, it could automatically trigger a highly targeted microsprayer right next to it to apply a tiny dose of the appropriate pesticide only where needed, or simply send a very specific alert, Colorado potato beetle detected in Sector 4B, back to the farmer.
Wow, precision agriculture enabled by local AI, minimizing chemical use, maximizing yield.
Exactly. These devices aren't just sensors anymore. They become truly intelligent, perceptive, and autonomous agents acting directly in the physical world thanks to edge AI.
Those examples really bring it to life. The smart doorbell, the offline voice commands, the pest detecting sensor. It shows how our devices can become genuinely intelligent and autonomous, not just connected conduits to the cloud. Okay, to wrap up our deep dive today, let's zoom out one last time to the bigger picture. Considering everything we've discussed, the shift from the cloud monarchy, the roles of fog and edge, the benefits, the use cases, the rise of edge AI, to conclude, what is the key takeaway about this profound evolution from centralized cloud models to a distributed architecture?
I think the single most important takeaway is that this evolution of IoT architecture, moving from that purely centralized cloud model towards this distributed continuum of computing with edge and fog, isn't just a minor tweak. It's really a necessary and powerful maturation of the entire Internet of Things concept.
Maturation, meaning it was bound to happen.
In many ways, yes, to unlock the full potential of IoT. We've seen throughout our discussion today how edge computing provides that almost reflex-like speed and critical operational autonomy right at the device level. We saw how fog computing offers that crucial intermediary layer for local coordination, aggregation, and maybe more complex processing within the local network.
And these complement the cloud, right? Not replace it.
Absolutely. They truly complement rather than replace the strategic long-term intelligence, the massive data storage, and the global oversight capabilities that the cloud excels at. This distributed approach isn't about rejecting the cloud, far from it. It's really about creating a synergistic partnership.
A partnership between edge, fog, and cloud.
Exactly. Leveraging each layer for its unique strengths, using the right compute resource at the right place for the right task. That's how you build a more resilient, vastly more efficient, and ultimately much more intelligent ecosystem.
So it's about creating a smarter, more efficient, more robust, and truly responsive ecosystem overall, unlocking capabilities that, frankly, were previously unimaginable with just a centralized cloud model.
Precisely. And the profound benefits we've spent the last while discussing, that dramatically reduced latency, enabling real-time control, the significant bandwidth conservation leading to major cost savings, the inherently enhanced privacy and security from processing data locally, the increased reliability through offline operation, These aren't just, technical bullet points.
They're more fundamental than that.
They are the keys. They are literally the keys unlocking a whole new generation of real-time mission-critical applications that simply couldn't exist or couldn't perform reliably or cost-effectively in a purely cloud-only world.
From the factory floor examples.
Right, achieving near-zero defect production through instant quality control.
To the smart healthcare devices.
Enabling rapid, life-saving interventions right in the patient's home. The impact of this distributed intelligence, this distributed mind, is already creating safer, more efficient, and more intelligent systems across practically every sector imaginable.
And the Edge AI piece feels like the next logical step in that progression.
It absolutely is.
Yeah.
The rise of Edge AI represents embedding sophisticated perception, reasoning, and decision-making capabilities into the very fabric of our devices, making them truly autonomous actors. So perhaps the final thought is this. The primary challenge in IoT is subtly shifting. It's moving beyond just connecting billions of devices.
To actually managing them.
Yes,
Yeah.
to securely managing, orchestrating, and extracting value from a vast distributed fleet of intelligent agents acting at the edge. That highlights that the future of IoT truly lies in this seamless, dynamic interplay between the edge and the cloud, creating a resilient, responsive, and genuinely pervasive digital intelligence woven into our world.
That's a powerful thought, to leave us with the shift from mere connection to the orchestration of distributed intelligence. It really underscores that understanding these distributed architectures, edge, fog, and their relationship with the cloud is absolutely essential for anyone involved in technology today, or anyone just trying to understand where our increasingly connected world is heading.
Indeed. It's a fundamental shift, and as you said, there's always more to learn. These foundational changes are really paving the way for innovations we can probably barely even imagine today.
Absolutely. And if you've enjoyed this deep dive into the architecture of modern IoT, you'll definitely want to tune in for our upcoming series. We'll be exploring data analytics and visualization for Internet of Things.
Ah, the perfect follow-on.
Yeah.
Once you have all this data being generated and processed at the edge and aggregated, how do you actually make sense of it all? How do you visualize the insights?
Exactly. We'll be delving into how we turn all that incredible data being generated at the edge, in the fog, and in the cloud into actionable knowledge.
It's the next critical layer of IoT intelligence, definitely, and it builds directly on everything we've discussed today about where that data comes from and how it's processed.
Well, thank you so much for joining us on the deep dive today. It's been a fascinating discussion.
My pleasure. Always enjoyed digging into this stuff.
And thank you all for listening. Make sure to subscribe to our channel, Tech AI and Beyond, for more in-depth explorations of transformative technologies like this one. We look forward to having you join us on the next deep dive.